Okay, so good afternoon. Yeah, so I wanted to review the cut and hopefully finalize, so give you the last tips for the last chapter. You already submitted the resolution, so I guess this will help you in your revision. So this is the cut that I gave you guys. Um, yeah, so the first, there were four questions. Are they? Yes. So you are required to perform the following things. So the first one where you asked to express some complex number to polar form, meaning that you're given the power. This number is an integer anyway, this year 2025. And then this is expressed in the XY form. The X value, the real value of the complex number, the real part, and then the imaginary part of the complex number. And so on. So here now, what I will do is I have solutions which are prepared for you, which we can go through very quickly. And so the first one is that one of expressing that power of a complex number in polar form. So what does that require you to do? Well, the first thing you need to do is find R. So you have Z is X plus IY, and then this is raised to power 2025. You need to move from here to polar form. Polar form just meant that you have R, the radius, and the Euler form of the function, which is cosine theta plus I sine theta. So x is 2 over root 2 and y is 2 over root 2. So meaning that r is usually x squared plus y squared square root. So x squared is just 4 over 2, and then y squared is 4 over 2. So that gives you the square root of 4, which is 2. So the radius r is 2. And then the argument, which is the angle for the polar form, this is usually the angle. You can think of it this way. If we go geometrically, we'll be saying, let me see whether we are able to zoom here. I'm not seeing those features, but anyway, fine. Let me see one moment here. Well, this is not PDF, that's why we're not able to do this. But anyway, yeah. So basically, the geometric form is to say that, you have the x value, which is 2 over root 2, and the y value, which is 2 over root 2. So you can write it in this form. This is your P, which is your, let me see, I'm able to do that. Oh, yes, I am. Yeah, so the geometric form was saying that this is your complex number, which we're calling our Z. And now we are expressing this Z raised to power 2025 into polar form. So we have found our R now. The angle is basically this one here. All right. This is just basically tan theta, which is 2 over root 2, the y value, over x value, which is 2 over root 2, which is 1. And basically, which angle gives you the same sine and cosine, because sine divided by cosine gives you 1. And that angle would be 45 degrees, as you can see here, which we can express in radian form. This is just pi over 4. All right. So now we go back to what we asked to do. So this 2025, this z power 2025, you can express it as r cosine theta plus I sine theta raised to power 2025. Now you replace the r and the theta, so you have this, which is in the form we wanted. We wanted it to have some r, which is 2 raised to power 2025. You can write it whatever number it is. And then the cosine of 2025 pi over 4 plus I sine 2025 of pi over 4. Here, how this comes about is what you call the Moivre's or the Moivre. I don't know how you want to pronounce it, but the correct way is the Moivre's theorem that says that when you are raising the power of this expression, Euler form, you just multiply the angle by that power. So you just pi over 4 times 2025, you get 2025 pi over 4. And that's it. You can leave the answer as that. Now, how did this come about from 2025 pi over 4 to pi over 4? Well, because 2025 is an odd number, which you can split into. The nearest even number would be 2024 plus 1. All right. And so plus 1, and then you can put in brackets times pi. All right. So this, if you divide by 4, the 4 disappears. So this will just be an integer. This will be a multiple of 2. And multiples of 2, when you are dealing with angles, angles are periodic. Periodic means that if I have an angle theta, then I can shift it by 2 pi and the copies of 2 pi. So basically any integer you multiply by 2 pi. I mean, what I mean by that again here on my screen, I could say this is my angle, you know. What do you want it to be? Well, it can be 0. The easiest one is 0 to deal with them. So if my angle is 0, if I go this way, I'm going minus 360 degrees, which is minus 2 pi. Or if I go the other way, I'm going the positive direction, which is 2 pi. So 0 degrees is the same as 2 pi or minus 2 pi. You can also decide to go around twice, so it is minus, 4 pi, or the other direction, which is 4 pi, and so on like that. Okay, that's why that happens like that. Okay. That was number one. Number two, you are asked to find, now we should be doing this together at par. So let's just close this one moment. We stop the annotation. All right. So the other one was question number two. So we're done with the first one. The next one was asking you to determine the multiplicative inverse of z equals 1 over 2 minus I root 3 over 2. So the inverse of multiplicative inverse means that what number you multiply by that non-zero number to get 1. I mean, for instance, the multiplicative inverse of 1 is 1 because 1 times 1 is 1. The multiplicative inverse of 2 would be a half because a half times 2 is 1, and so forth and so on. Now that is as far as integers is concerned, but now as far as complex numbers is concerned, you see complex numbers have the real and imaginary part. So it means that we'd have, it's just, now let's go to the solution here. So the inverse of z, which is 1 over z, all right? And now here we are bringing in division of complex numbers, which means we need to bring in complex conjugate. So z inverse, our z is just 1 over this number. And this number being a complex, you can multiply, or you should multiply by the complex conjugate of the denominator. So the complex conjugate of 1 over 2 minus I root 3 over 2 is 1 over 2, a half, plus I, the square root of 3 over 2, divided by the same number. Now, if you expand, numerator is just a half plus I root 3 over 2. Now, what happens to the denominator? Well, if you multiply out, you end up with a half times a half is a quarter. And then you multiply minus I root 3 times I root 3 would be minus, it should be minus I squared 3 over 4. But then I squared is minus 1. So this becomes 3 over 4. So a half plus 3 over 4 is 1. Then a half multiplied by this plus negative of this times a half disappears. So the denominator is 1, in other words. And we're done with that one. Number 3 was asking you to determine the fourth roots of z equals 1 minus I. So how does that go about? Well, now we need another. Let's close this and go to the next one. So the next solution is this one here. And we need to clean our board, but okay, fine, no worries. Yeah, so now the fourth roots for complex numbers. One moment here, let's just clean this our board here. I don't know if this can be seen. Oops, sorry. Okay. How did I do this? I want to zoom. I don't know if you can see it. But okay, fine. So determine the fourth roots of z equals 1 minus I. This is our complex number. Again, it's always good to sketch it. So if you sketch it, geometrically you have 1. This is the real part is 1. So 1, you measure that distance length. And then the I part, the imaginary part is minus 1. So minus 1 is below here. So this is your complex number, z equals 1 minus I. So if you want to find the roots of z, which is r cosine theta plus I sin theta, obviously you need to find r. Now, our x is 1, our y is minus 1. So 1 squared plus minus 1 squared is 2. You find the square root, you get the square root of 2. So that's our radius, r. Then the angle, here I actually, by just sketching, I showed you what the angle is. Obviously, well, we can go the other way of finding tan theta equals y over x. It will just be minus 1 over 1, which is minus 1. Then tan inverse of minus 1. Now, if you punch in your calculator, it will give you something that is not exactly what we want because angles are shifted because of the periodicity. And so now we will just, when you sketch, you can tell where it is. You can see. So this triangle here is right angled isosceles triangle, meaning what? That these two sides are equal because this length is 1, this is minus 1, this length is 1. So here this is 90 and this one is 45 and this 45 degrees. So our theta is 45. That's the measure of the angle, but where is it? This is in a negative word. So our theta is minus 45 degrees or minus pi over 4 or 315. Remember the periodicity that now if you add 2 pi, you go around from here, you go this way. I mean, you go this to get here, you go around like this. So it is 360, which is 2 pi, plus minus 45, it gives you 315 degrees, all right, which is 7 pi over 4, by the way. So the roots now will be, the roots will be given by this formula, which is, I can call it omega k, the nth root of r, in this case is the fourth root of r, cosine theta plus 2 pi k over n, our n is 4. So when k is 0, you have w0, you plug in here. This is fourth root of the square root of 2 times the cosine of, here, you plug in theta is minus pi over 4 plus 2 pi k. What does that give you? Well, k is 0, so it's just minus pi over 4 over 4. It's minus cosine of minus pi over 16 plus I sine of the same angle. And we are done with that one. Next, when k is 1, then we have omega 1. So again, you go back here, you have k, the omega 1 is the nth root, n is 4, so it's the fourth root of the square root of 2. I don't need to expand it. If you wish, you can punch in your calculator, get an exact answer. But it's still satisfactory. It's an irrational number, so there's no problem, all right? Cosine of minus pi over 4 plus 2 pi over 4. Well, so if you expand that, this becomes 4 times 2, 8, minus 1 is 7. So it's cosine 7 pi over 16 plus I sine 7 pi over 6. And so forth and so on. I mean, we're just now plugging into a formula and we get our answer. I don't believe that that is too complicated for you. If it is, of course, you will tell me. All right, number 3, or I don't know. Yeah, Roman 3 was an interesting problem. You're supposed to graph this region and describe it in words. So even before I show you the solution, you can guess, I mean, what this looks like. I mean, when you have, let's just write this down here. When we have something like this, modulus of z equals, say, some number, let's say 1, all right? Well, this is, you remember modulus of z is the square root of x squared plus y squared square root equals 1. If you take the square root to the other side, this becomes x squared. Well, let's write it down. It's x squared plus y squared equals 1. And what is this? Well, this is a circle with the center 0, 0, the origin, whose radius is 1. So this is what this describes. So we go back here to what we asked to describe. Well, this is just a circle whose radius will be I, is shifted by I, z equals I. And so now we have two radii. One is 1, the other one is 2. So when modulus of z minus I equals 2, it means that it's a circle centered at I, whose radius is 2, like this. And then when it's 1, it means that we'll be talking about the circle centered at I, whose radius will be 1. And now here we are having inequality. We're not having equality. So in one case, we are talking about less than. So we'll be looking at the bigger circle, whatever is inside, and the smaller circle, whatever is outside, because this is greater. All right? So here I give you the description. Oops, one moment. Here again, we need to remove the annotation here. So I take this first to show you the solution. So the solution, this is number 3 slide, all right? Third slide. So this turns out to be, well, I need to erase this one moment again to clean our screen. So basically, the first part, I would say these are two regions. One is modulus of z minus I is greater than 1. So this is a circle that we are considering whatever is outside the circle because it's greater than 1. So this is the circle. And then modulus of z minus I equals 2. We're considering the circle centered at I, whose radius is 2. You can see 1, 2, 1, 2. And we're looking at the outer, well, the inner part of it. So for this one, the outer part. So this one, the outer part. This one, the inner part. This gives you a ring, what we call an annulus. And we're done, the shaded region. Good? Very good. Now, in one of the lectures, I believe, a while back, we did look at these kind of things, regions or sets in the complex plane. We had annulus or annuli. We did have, I don't know, when we were sketching two graphs in the XY plane and the UV plane, etc. There's the next question coming up. So part E, to finish this question number 1, was asking you to, yeah, so we finished A, B, C, D, E. So the part E, we can even say without going to our slide, but I'll show you anyway briefly. So give an example for each of the following. An analytic function that is not entire. Actually, the example I've given you is wrong. I didn't check completely the answer, the question. So here I'll give, I will not show you that slide because it is wrong. I've just realized it anyway. So an analytic function that's not entire. So here we need two concepts. One, what is an entire function? Two, what is an analytic function? And then I will negate one of it. So you can find an analytic function that's not entire. Is that possible? Well, so what is analyticity and what is entire of a function? So I don't remember, but I believe that I've shared with you some notes about what an analytic function is and an entire function is, but I just remind you. So we talk about differentiability of a complex num function f of z. And then in mathematics, we write a lot. So here, let's just sketch on the screen. So we do have our function, which is f of z, right? Which is basically mapped between two complex sets or subsets of C. So we say that this function is differentiable. We were talking about the existence of the limit of f of z plus del z divided by minus f of z divided by del z as del z goes to 0. If that limit exists, when we're considering along the real line or real axis, the imaginary axis, we talked about the existence of that limit being unique, and so we were talking about it being differentiable. So now, if a function is differentiable at a point and within every neighborhood of that function, then we call that function analytic. So basically, analyticity carries differentiability at a point and at the neighbors of that point. All right. And so the best examples we were giving, or I gave, were when you think of a line, or you think of, I can just say f of z. Now, f of z, I can just say something like z, then this function would be analytic. If I say f of z squared, well, this function turns out to be differentiable. You can differentiate the derivative of this just to z, and so on. Now, if I say this, I can say this one divided by maybe, I don't know, z power 3. I don't know, something like this, minus 1. Then this function will be analytic except when the denominator, the values of z are 0 or 1, because 1, z equals 1, you'll have 1 cubed minus 1 is 1, minus 1 is 0. So at that point, this function will not have a derivative. Okay, so differentiable. So now you're supposed to give a function. So an example of an analytic function that is not entire. So if a function is differentiable at a point and within its neighborhood, then that function is analytic. Now, if it is analytic, that means differentiable everywhere and in all its neighborhoods in the whole complex plane, then that function is said to be entire. So, is it possible to get a function that's not entire but it's analytic? And the answer is yes. This one here, this function is actually analytic for all complex numbers except when z, rather the values of z for which the denominator of this function is 0. So this function, had it been something like z squared, f of z equals z squared, this function is entire because it is differentiable at any complex point, basically all the neighborhoods of any point in the complex plane. And so this function will be analytic everywhere in C, so it's entire. This function is not entire. Entire means that there is no exception for its analyticity. So there you have a good example. In fact, I can just give you, so you to be able to generate many examples, just think of, in general, any rational function. You know what a rational function is? That it has a numerator and a denominator. So as long as the denominator has no 0 values for z values, then that function would always be analytic. And so, yeah, so there you have an example. Now, an example for a nowhere differentiable function. Now, let's just define. So here now we are playing around with three concepts. One is differentiability, two is analyticity, and three is entire. I don't know whether I should say entireness or entirety of a function. But anyway, so, and they are all relying on each other, that you can find a function that's differentiable at a point, but it's not differentiable at its neighbor, at the neighbors. So it would fail to be analytic. And of course, it would fail to be entire. Now, you can find a function that's differentiable everywhere within, I mean, at a given point, within the neighborhoods or near the neighbors, but not in the whole complex plane. In that case, it will be analytic. And then now the last one is if it satisfies all those properties. It's differentiable at a given point for all neighbors and in the entire complex plane, it's entire. So can you give an example of a function that's nowhere differentiable that fails for all the three? In fact, I do believe we did an example last time, but I just give you a quick example. I just say, I call it h of z. And remember, z is a, well, I mean, we define z, our complex number or value that relies on the real part and imaginary part. So I can just say x plus x minus 3 I y. This function is nowhere differentiable. How do you know? How will you know? Two things you can do. One, you can find the limit of this function. As you approach zero even, or at any point you'll pick. It turns out that it will not exist. I mean, along the vertical axis, the limit will be 1. Along the horizontal axis, the limit will be minus 3. And so it will not work. All right. So there it is, ladies and gentlemen. Now let's finish up. I didn't want to take too long in this review, but this review is more like a continuation of the other lecture. So let's look at the next set of questions here. So question 1 is done. That's it. 30 out of 30. Question 2 is an interesting one. It was asking you to determine the following. One, the image of the real part of z equals 1 under this map, f of z equals z squared. Then the second thing you're supposed to do is sketch it and use words to describe it. And then part B was, this is, I think this you already have, so I'm not going to give you too many details about it. Probably I'll just show you the slide so that you can, replay it and see, hopefully, as you review. So, how do we go about this? Well, we'll say that, let me just open the slide so that I don't have to draw too many things that I don't need to draw. All right, so the real part of z, remember z equals any complex number is expressed in terms of a real part, which is x, plus the imaginary part, which is y. So z equals x plus iy. So we just say real part of z, which is x, equals 1. So that just means it's just a line x equals 1. So how do we sketch that? Well, we have our xy plane, the real axis, the imaginary axis. You look for the value of x equals 1 and that line. The value of y is anything from minus infinity to positive infinity. So this is what we are looking at in the xy plane or the z plane. Now we apply the map. The map is f of z equals z squared. So we'll have f of z equals z squared. Z is x plus iy. So if you square it, what do you get? You open binomially, you end up with x squared minus y squared plus 2ixy. And now our function is always the same way. You have a complex number z is x plus iy, real part, imaginary part. Same way you have for the complex function, you have u plus iv. U is a real part of the function, v is the imaginary part. So the output here is x squared plus y squared. That has no I, so that is the u value. And then 2ixy corresponds to v. This one, iv. So v is 2xy. And since we are looking at x equals 1, so if you plug in x equals 1 here, you get u is 1 minus y squared, and v is 2y. And now we can get rid of y. We just say y is v over 2. Plug in this one into this function. So it turns out that u equals 1 minus v squared. And so this is the image of the real part of z equals 2 under our mapping f of z equals z squared. Now remember, complex functions cannot be drawn on the same graph as as a complex number because it's a four-dimensional function. And so we are only, I mean, the graphs we've been dealing with, you imagine 2D is what you are seeing on the screen, XY. The 3D, you play around again in space and you watch movies and stuff like that. Now 4D is not possible. So we just separate the two axes. We have the X plane, which is this one, and now we sketch this one in the UV plane. So how do we do the sketching? Well, this is all we do. So the values of U and V. So when U is 0, we plug in 0 here, then U is 1. When V is 0, U is 1. When U is 0, well, you have 0 equals 1 minus V squared. So V squared equals 1. I mean, V squared over 4 equals 1. So V is plus or minus 2. You can check that. I mean, when V is 2, you have 2 squared, 4 over 4, 1. 1 minus 1, 0. And so on. So when you sketch, it turns out to be looking like this. 0, 1 value for U, then 0 for V. And then when U is 0, V is 2 and minus 2. And this is a parabola. So the description in words is that the image of the line real part of Z equals 1 under this mapping F of Z equals Z squared is a parabola, which is what you have sketched. Are we done with that one? Yes, we are. Next is, what was the next question asking you to do? Well, this one I was claiming that I believe you do have the solution somehow, but let me just give you a quick sketch of it. So that I move to the next thing. I didn't want to make this one long, but okay, fine. So what do we have? Well, actually, this is called the triangular inequality for complex numbers. And here I've played around with something. What? I mean, I could just say Z1 minus Z2. Now I'm looking at minus, so I can just fix this minus Z2 to be plus Z3, some other complex number. You know why I can say that? Because for every complex number I have, I can always talk about is additive inverse. 1 plus I is a complex number. Minus 1 minus I is complex inverse. So I can do that, but anyway, I didn't do it. I just worked it out as it is. So modulus of Z minus of Z1 minus Z2 is less or equal to modulus of Z1 plus modulus of Z2. So one of the things you need to recall is the definition of modulus, so absolute value for a complex number. If you square, you get the complex number times its complex conjugate. I mean, you just take Z equals X plus IY times its complex conjugate, which is X minus IY. You will end up with X squared plus Y squared. And this turns out to be the modulus squared because the modulus is the square root of X squared plus Y squared. So that's the first step we apply. So the modulus of this on the left-hand side squared equals the complex number you're dealing with times its complex conjugate. Next, well, complex conjugate is linear, so it's just Z1 minus Z2 times modulus of the complex, complex conjugate of the difference of these two numbers is the same as the complex conjugates, then you take the difference. So you apply complex conjugate to Z1 minus complex conjugate to Z2. And then now you apply binomial expansion, you just multiply out. You get Z1 multiplied by this guy, you end up with this, and then minus Z2 times this guy, binomially, you end up with this. And next, now, Z1 times complex conjugate of Z1, apply the same thing we had here. This is modulus, the square of the modulus of Z1. Likewise, Z2 times the complex conjugate of Z2 is the square of the complex, the square of the modulus of Z2. All right? All right, now here again, let's see whether we can do this. One more thing here. Been trying to do, but this thing is not allowing me, but anyway, fine. Yeah, anyway, next, now this middle part, I just played a little bit. So let me give you quick arguments to say that, so that you have modulus, square of modulus of Z1, minus, I pull out the negative, I just have the sum of these two guys, plus the square of Z2. Now, something I've not mentioned, which I can mention now for you, is that here when you did this, you got Z1 times the complex conjugate of Z2 minus Z2 times complex conjugate of Z1. It turns out that this number here is the same as, because of the complex conjugate of the complex conjugate of Z is Z. In other words, if you apply complex conjugate twice, you go back to the original complex number. So here we have Z1, we have Z2 times Z1. So if you apply complex conjugate to this guy, I get this one. So that's why I have complex conjugate of this one will be complex conjugate of Z1 times Z2, which is this. So that is the same real number. I mean, is the same complex number plus its complex conjugate. In other words, this is like Z plus by Z. By Z is complex conjugate of Z. So here I have Z plus by Z. And now if you take Z plus by Z is X plus IY plus X minus IY, you end up with 2X, which is twice the real part of Z. So now I replace these two guys by, this becomes now minus 2 real part of Z1 times complex conjugate of Z2. Then one other thing that for you to notice when we conclude this one is that the real part of Z, which is X plus IY, which is X, is less or equal to the square root of X squared plus Y squared. Because if I fix Y to be 0, I'll be talking about the square root of the square of X, which equals this guy. But now this becomes bigger. And what is this? This is modulus of Z. So I wanted to relate the real part of Z and the modulus of Z. So now we can replace. Now we're ready to replace yet? Not yet. I just want to say one more thing. So this is a number which is less than this one. So what do? I replace this part by something bigger. Why? How sure am I it's bigger? Well, because the real part of Z is less than modulus of Z. A modulus of Z is already a positive thing. So I'm adding. So this is minus, but now I'm adding. So here you are subtracting, here you are adding something bigger. So this becomes less than this. So this is bigger. It's greater than or equal to. And now once we're here, so we have modulus of the product of two complex numbers, the same as the individual products of the two complex numbers. So this equals this. And that's it. You just factorize, you end up with the square of modulus of Z1 plus modulus of Z2. So this left-hand side equals the right-hand side, and that's it, ladies and gentlemen. Now, lastly, this I can talk about very quickly so that I don't waste too much time on this. I just want to say now, number 3 was asking you to prove that the set of complex numbers is a field. So here again, I already told you, I don't need to show you, but maybe I can at the same time. But I just tell you that, look, what's a field? A field is just a set where you can perform the 4 basic operations. What are the 4 basic operations? Well, they're just addition, subtraction, multiplication, and division. Now, when you say where we can perform, well, what does that mean? It just means that whenever I pick 2 complex numbers, I add, I get a complex number. Whenever I pick 2 complex numbers, I subtract, I will always get a complex number. Whenever I pick 2 complex numbers, I divide them with each other. As long as I'm not dividing the one below, the denominator by a 0, I get a complex number. Likewise for multiplication. All right. So, this I already mentioned to you, but I just show you and then I leave the slide. So when you are reviewing, you will just, figure it out. So for all Z1, Z2, Z3, any 3 complex numbers I have, this is possible. I can add, subtract, multiply, divide. So addition and subtraction, you just do it straight away. I think I don't need to comment on that one. Multiplication, you remember multiplication of complex numbers. So the one I will comment about is the division, which brings in the complex conjugate. And when we say that we can add, multiply, subtract, divide, what we are saying is that you can always express whatever you get as the product or the solution as a real part, imaginary part. It has an I part and a part with no I. And that's basically what you did here. And that's it. Then number B, we are looking for roots, complex roots of, the fifth. These are actually 5 fifth roots of this complex number. So again, this will just repeat like you did number 1. So I just demonstrate for you very quickly. I just say what you will do. You need to find it in polar form. You find theta and you find r. And then you substitute it in this. The nth root of r times the cosine theta plus 2 pi k over 5 plus I sine, 2 theta plus 5, like that. And that's it, ladies and gentlemen. So I will not go into so much that repetition of that because that's the same thing we did in question 1. So let me talk about the last question, which is question 4, which is now touching on a number of things which are interesting. In fact, here I would wish to, well, actually, maybe I don't. I was going to go to Taylor series and stuff, but for now, maybe I don't need to do that. I'll just tell you. So let me see, which slide are we on? Number 6. Let's see. Oh, no. Okay, let's see whether it will go to the next one. Does it go to the next one? Yes, it does. Yeah, so this is it. Yeah, so actually to prove number 4a, which says show that e raised to power z minus 3 pi I equals e raised to z plus 3 pi I, all you need to prove is that minus 3 pi I equals 3 pi I. So one thing you can do is just mathematics. Mathematics just means that you assume that they are equal, then you should not get something ridiculous. So that means if this left hand side equals the right hand side, then what happens? You work it out. This is just a power of something with the same base. So e raised to z times e raised to minus 3 pi I. The right hand side you have e raised to z times e raised to 3 pi I. And then this is just 1 over e raised to 3 pi I equals e raised to 3 pi I. So it goes to the other side, it becomes e raised to 6 pi I equals 1. But then 6 pi I, we already said is just what? You can write it as cosine 6 pi plus I sine 6 pi. So 6 pi is a multiple of 2. It's just 3 copies of 2 pi. And 2 pi is just 360, 360, 360. So this is the same as cos 2 pi, which is the same as cosine of 0, which is 1. And that is not ridiculous. It's true. So this is true. That's one way of arguing this one. How else can you argue this one? Well, you can just say that angles are periodic. What does that mean? Theta is always given by theta plus 2 pi k, where k is an integer. Integers are 0, plus or minus 1, plus or minus 2, plus or minus 3, up to infinity, and so on. So if theta, in this particular case, is minus 3 pi, well, then we can shift it by a multiple of k that will give you 3. What is that? When k is 3, you have minus 3 pi plus 2 pi k, but k is 3, so it's 6 pi. So 6 pi minus 3 pi is 3 pi. So minus 3 pi is same as 3 pi because of the periodicity of the angles. And so this is true, that relation. Good? Very good. Now, the last thing for me to say here is limit. So find this limit. The limit of z squared minus 4z plus 4 over z squared minus 2i as z approaches 1 plus I. So the first thing you do is just plug in 1 plus I into the function. If you plug in, you will get 0 over 0. So you'll apply what we used to use in previous calculus. It was called L'Hopital's rule. That means you differentiate numerator, differentiate denominator. If you differentiate denominator here, you just get 4z minus 4, which is this, divided by, you differentiate the denominator, you get 2z. Now you plug in again. And if you plug in again, you end up with 4i over 4 plus 2i, which simplifies into 2i over 2 plus I. And then the requirement was you express your solution in algebraic form. So algebraicity of this requires you to multiply with the complex conjugate. And this ends up being 2 plus 4i over 5. So the real part is 2 over 5. The imaginary part is 4 over 5. And that's it, ladies and gentlemen, as far as what was required was done. So the last part here is to show this is nowhere differentiable. That's an interesting one. Yeah? So let me go there. Now, I think I opened the wrong one. All right. That one just requires you to use what you call the Cauchy-Riemann equations. So briefly and quickly, given a function, you can always check whether it's analytic. So you need the Cauchy-Riemann equations. That means the partial differential derivative of u, the real part of the function, with respect to x, should be equal to the partial derivative of v with respect to y, and the partial derivative of u with respect to y should be equals to negative the partial derivative of v with respect to x. And so now we comment the following. So if these two Cauchy-Riemann equations hold, then the function is analytic, and therefore it's actually differentiable with the exception of whatever, the function accepts. If they hold, the Cauchy-Riemann equations are true for some values, then the function may be analytic for those regions that we remove the exceptions, or may be differentiable somewhere. And if they don't hold at all, then the function is nowhere differentiable. So all we did is just find the derivative, these partial derivatives, and compare them. So del u del x, using the quotient rule, will be y squared minus x squared over x squared plus y squared squared. That means you hold the numerator, you differentiate the numerator, you get 1 times x squared plus y squared. This is what we did here. Minus, now you differentiate denominator with respect to x, you get 2x times x is 2x squared, and then that's how you end up with this. Likewise, to differentiate the other one here, you hold, again, you do the same thing, and you end up with this. And now you can see these two are not equal. Y squared minus x squared over this, you can see the denominators are the same. So numerators is negatives of each other. So when it's like a equals to minus a, only when a is 0. But when a is 0, that means x and y would be 0. This function will not have the derivative existing. So this will never be equal. Likewise, for the other part, if you find the Cauchy-Riemanns now for del v, del y, and del u del y, del v del x, del v del y, you end up with this. Minus 2xy, they are equal. Del u del y equals del v del x. But the requirement is that they should be negatives of each other. So again, this will never be equal. So the function is nowhere differentiable. And that's it, ladies and gentlemen. So the last slide, which is in 1 minute, I finish, is just to talk in general about some things that now you can review about, but I've done as far as the CAT is concerned. I've given you a good review. It's just now some interesting functions here. This is a complex trigonometric functions, specifically sine and cosine in relation to the exponential function. So EIZ is cosine z plus I sine z. Then e power minus iz is cosine z minus I sine z. So if you add these two guys, the left-hand side is eiz plus e power minus iz. The right-hand side, you can see these two disappear. You end up with 2 cosine z. So cosine z is a half eiz plus e minus iz. If you subtract, the left-hand side will be eiz minus e minus iz, which equals cosine z minus cosine z is 0. Then I sine z minus I sine z is twice iz. So if you make sine z the subject formula, you end up with a half, 1/2i times this expression. And then the last thing for me to say is now the Taylor series for this is, you remember that the exponential value raised to power x, this is a Taylor series, so it's equals to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x power 4 over 4 factorial, and so on. So if we replace x with iz, we have the Euler formula, which is cosine z plus I sine z. But now we can expand this one using this. We have e raised to iz raised to power 0 plus, instead of x, you put iz plus iz over z squared over 2 factorial, and so on. So now you separate the ones with real part, the ones with no I, and the ones with I. So it turns out that you will end up with 1 minus z squared over 2 factorial plus z power 4 over 4 factorial minus z power 6 over 6 factorial plus so many terms, plus other terms that will have z. If you pull out the z here, you'll have I, then you have z minus z cubed over 3 factorial plus z power 5 over 5 factorial minus z power 7 over 7 factorial, and so on. So the ones with I correspond to sine z. The ones without I correspond to cosine of z. And these are the Taylor series for cosine z and sine z. Ladies and gentlemen, that's about it. Now, for the questions, I think you will address them with me. But now, for now,